Okay, so this is Mrs. Sharp, and we're going to go over Learning Target 1.7, either again for those of you who saw it in class or for the first time for the 6th and 7th hour classes who did not have time to get through this. So basically there are 3 things that I would like for you to take away from 1.7, and those things are that I would like for you to identify the correct units of measurement for volume, mass, length, temperature, density, amount, and time in the SI system. I would like for you to be able to see. I'm trying to change my color here. I would like you to understand the difference between a base unit and a derived unit. And then finally, I would like for you to be able to use the SI prefixes. So those are the 3 basic things I'd like for you to be able to do with this learning target. So let's get started. Alright, so first things first, this SI system that I'm talking about is the International Unit System for reporting data. Actually, the SI system is SI because it stands for System International, which is French, and it's some kind of an accent mark on there, either up or down. I guess I'm not really qualified to make that call, but it's what we should use internationally to report data. The reason it's so important is because if we don't use these units for making measurements, our units are incomprehensible to other people around the world. So we want to have a consistent system where scientists around the world know what one another are saying. There are 2 types of units that I would like for you to know the difference between, and those are base units and derived units. So base units are a defined unit based on an object or event in the physical world. It is independent of other units. Here are some examples of base units, and you have these in your notes. The first one is the base unit for time, which is the second. Pay careful attention, please, to the capitalization on these. So symbol is a lowercase s as opposed to an uppercase. The next base unit we have is the meter, lowercase m. That measures length in the SI system. Then we have the kilogram for mass, which is kg. We have temperature in degrees Kelvin. Note that there is no degree sign in front of the K. Amount in moles, and the abbreviation for mole or moles is MOL. And then these last 2 I'm not going to assess you on, but I thought we'd throw them in there. Electric current is the amp, capital A, and luminous intensity or brightness is the candela or CD. Now all of these units are independent of other units, meaning other units don't define them. They are standalone units in the sense that they just are what they are. So a second is a second, and that might be used to define other units, but other things don't define a second. A second is simply the amount of time between a radioactive cesium atom emitting radiation. That sounds pretty random. Somebody just decided that that was going to be a second. So those are base units. This is an American replica of the true kilogram, which the true kilogram is in France in a museum, and then there's an American replica. So this is the kilogram. It seems sort of random, but this is what we use to define a kilogram, not another unit. So we also have derived units, units that are defined by a combination of other units. I like to think of it maybe not by a combination of, but just by other units. So I'm going to cross this off. So units that are defined by other units. So they're not based on a physical event or an object like the kilogram. They are defined just by other units. So the first good example that I have for you is volume. Now volume is defined by 3 length measurements. So if you were going to measure, for example, the sides of your desk, the volume of your desk, you do length times width times height. Length times width times height. And you might choose to use centimeters to measure each one of those. Now if we treat units like a variable, like an x, and we multiply x times x times x, or centimeters times centimeters times centimeters, we're going to get centimeters cubed. So that is a defined unit, but because it is defined by other units, in this case the centimeter. Along with that, the milliliter is defined by a centimeter cubed, because somebody decided that 1 centimeter cubed was going to be exactly equal to 1 milliliter. So a milliliter is a defined unit because it is defined by the centimeter cubed, another unit. Another example of a derived unit is density. So you can see density is defined by actually two different units, grams per milliliter and grams per cubic centimeter. So the density unit, in this case, is a combination of other units, and it's two different units. The grams per milliliter designation is most often used for when the volume of whatever you're finding the density of is a liquid, and cubic centimeters might most commonly be used for a solid. But since milliliters and cubic centimeters are equal, it really doesn't matter which one you want to use. The final derived unit we want to talk about is degrees Kelvin, and notice again that that K does not have a degree sign in front of it. Degrees Kelvin is simply degrees Celsius plus 273, or degrees Celsius equals degrees Kelvin minus 273. Now the reason Kelvin is our base unit and degrees Celsius are a derived unit is because degrees Celsius are defined by degrees Kelvin in the sense that degrees Kelvin reflect the existence of absolute zero at its 0 point. So at 0 degrees Kelvin, that's absolute zero, and that's where theoretically molecular motion would stop. And just so you guys know some helpful information here, water is going to boil at 100 degrees Celsius, so that would be 373 degrees Kelvin, again, no degree sign, and water freezes at 0 degrees Celsius, which would be 273 Kelvin. Now what's nifty about these is if you look about how far apart they are from one to the other, they're both separated by 100. So a degree in either system is worth the same amount. If you go up a degree in Celsius and up a degree in degree Kelvin, you go up by the same amount. But they're just 273 degrees apart. If you go up a degree Fahrenheit and you go up a degree Celsius, you're going up different amounts. You're going up more when you go up a degree Celsius than you are going up a degree Fahrenheit. Okay, here are the prefixes that I want you to know. So it's simply going to be copying this chart down. Now in your notes, you have a column off to the side that says equality or conversion factor. You only really need to fill in one column, and that's what I have here. So I'm going to put these up and just talk about them quickly. Then you're probably just going to want to pause it and get them copied down so that you can use those conversion factors. And then that'll be it for these notes. So here we go. We're going from biggest to smallest. So the biggest metric prefix I want you to know in this class is the giga. The giga is symbolized by a capital G. So if you have 1 giga something, that means you have 1 billion of whatever it is you're talking about. So for example, if you wanted to talk about a gigagram, then that would be capital G, lowercase g. So 1 gigagram would be 1 billion grams. Next we have the mega. Mega is capital M. So 1 mega something would be equal to 1 million of whatever it is you're talking about. So maybe megameters. So you can see how important it is that meters are lowercase. So we have 1 megameter would be equal to 1 million meters. But again, you could substitute any of these base units for that, or even moles are a base unit, or seconds. But meters, liters, and grams are the most common. Then we're going to jump into some more common looking ones, I hope. So you have the kilo. 1 kilo is 1,000, so 1 kilogram is 1,000 grams. A hecto, which is 100, so 1 hectogram would equal 100 grams. And deca. So 1 decaliter would be 10 liters. And that's one reason that the metric system is so beautiful, is because it goes by these factors of 10, which make it nice and neat. Now, smaller than a base unit, I would like for you to know deci, centi, and milli. Now, notice that anytime you say an E, you're smaller than the base unit. So deci is 1/10, or in other words, 1 gram is equal to 10 decigrams. So they're tiny. Centi, 1 gram is equal to 100 centigrams. So there's 100 in 1 gram. And milli is 1/1000th, so 1,000 milligrams in 1 gram. And then there's one more I want you to know called the micro. And the micro is this funny backwards looking Y thing. And 1 microgram is 1 millionth of a gram, so 1,000,000 micrograms in 1 gram.